All right, welcome everyone. Today we're diving into one of the most, I think, elegant techniques out there in competitive programming and computer science, the sweep line algorithm. So you see all these different geometric puzzles, and they might look pretty complex, right? But what if I told you that a single, really intuitive idea can crack a whole class of these problems, the exact kind you're going to see in exams and technical interviews? Well, that's exactly what we're going to break down today.
Okay, so here's our game plan. We'll start with the basic sweep line idea. Then we'll see it in action, finding intersections, the closest pair of points, and building a convex hull. And we'll wrap up with your very own algorithm toolkit.
All right, first up, the sweep line idea. It's really all about processing events in the right order. And to get this, we're not even going to start with geometry. Let's use a super simple example that'll make everything else just click.
So, here's the challenge for you. Imagine you have a list of when employees come into the office and when they leave. How would you figure out the peak attendance? You know, the absolute maximum number of people who are in the office at any single moment.
Okay, here's some sample data. We've got John, Maria, Peter, and Lisa, with their arrival and leaving times. Now, here's the big idea, the core insight of the sweep line algorithm. Stop thinking about these as intervals of time. Instead, think of each arrival and each departure as a distinct event that happens at a specific point on a timeline.
And that brings us to the core framework. Seriously, you're going to use this for every single sweep line problem. It's a super simple three-step recipe. First, you define your events, in our case, an arrival or a departure. Second, you sort all those events, usually chronologically. And third, you just sweep through them one by one, updating some key piece of information we call the state.
Okay, let's see this in action. We've sorted all our events. The very first thing that happens is at time 5, Lisa arrives. So our current count of people in the office goes up to 1. Next up, the clock hits 6. Maria arrives. Boom, our count is now 2. And then at time 10, John walks in. Our count hits 3. And this is important. We need to keep track of the highest number we've seen so far. So 3 is our current maximum. So we just keep going. At time 12, Maria leaves, count drops to 2. At 13, Lisa leaves, count drops to 1. You get the idea. The highest our counter ever got was 3, so that's our final answer. Now, for an exam, this next part is critical. You have to talk about time complexity. We have n employees, so that's 2 n events, an arrival and a departure for each. Sorting those takes O of n log n time. Then walking through them is just one pass, so the whole thing is dominated by that initial sort. That's how you get O of n log n. All right, you've got the basic idea down. Pretty neat, right? Now let's take this concept and apply it to some actual geometry. Our first challenge, finding intersections. Okay, just like with the employees, step 1 is always defining our events. Imagine a vertical line sweeping from left to right across the plane. What are the interesting points it's going to hit? Well, it'll hit the left endpoint of a horizontal line. Let's call that a horizontal start. It'll hit the right endpoint, a horizontal end, and it'll hit an entire vertical line segment all at once. So here's the puzzle. The brute force way is to check every single vertical line against every single horizontal line. But that's slow, right? O of n squared. We can do way better. The real question is, when our sweep line hits a vertical line, how do we efficiently figure out how many horizontal lines are currently crossing it?
And this, right here, is the aha moment. This is where the magic happens. Our state, remember that? It's not just a simple counter anymore. It's a data structure, something like a balanced binary search tree, that keeps track of all the active horizontal lines. So when our sweep line hits a horizontal start, we add that line's y-coordinate to our structure. When it hits a horizontal end, we remove it. And when we hit a vertical segment, we just query our data structure and ask, hey, how many active lines do you have between this y-start and this y-end? And because we're using the right tool, that query is super fast.
Okay, next up, finding the closest pair. This is another classic. You're given a bunch of points scattered on a plane, and your job is to find the 2 that are closest together. And you guessed it, we're going to use our sweep line to beat that slow brute force check.
So, the strategy is pretty similar. We start by sorting all the points by their x-coordinate. Then, as we sweep from left to right, we're going to keep track of a variable, let's call it d, which is the smallest distance we've found so far. Every time we get to a new point, we only have one question to answer. Could this new point, paired with something we've already seen, give us a distance smaller than d?
And here's the real magic. This is the key insight. We absolutely do not need to check every previous point. Think about it. For a point to be a potential new closest pair, it has to be closer than d, right? That means it must be in a narrow strip of width d to the left of our current point. And not just that, it also has to be within d vertically. This incredible optimization means we only need to look for candidates in this tiny d by 2d box. It's a huge reduction in work.
So why is this so efficient? Well, it turns out, and you can prove this geometrically, that that little box can only ever hold a small, constant number of points. It's not going to be crowded. So for each of the n points we process, we're not comparing against a growing list, we're just checking against a handful of neighbors. And that's what takes us from a sluggish ON squared all the way down to that beautiful ON log n we love to see.
Okay, for our last big example, we're going to look at building a convex hull. Some people call this the rubber band problem. This one uses a really clever variation of the sweep line idea known as Andrew's algorithm.
So what even is a convex hull? The definition is the smallest convex polygon that contains all the points. But honestly, the rubber band analogy is the best way to think about it. Imagine all your points are nails sticking out of a board. If you stretch a rubber band around the whole set and let it snap into place, the shape it makes is the convex hull. So how does Andrew's algorithm work? First, like always, we sort the points by their x-coordinate. Then we build the hull piece by piece. The rule is simple. As we add points to our hull, we must always be making right turns. If adding a new point forces us to make a left turn, that's a problem. It means we've created a dent, and the previous point we added wasn't actually on the outer edge. So we have to backtrack. We pop that last point off the hull and check again. We keep doing this until our path is only making those nice, outward right turns.
Okay, let's wrap this up. We've seen how this one powerful idea can solve a bunch of different problems. So let's put together your algorithm toolkit, the key takeaways you'll need for your exams.
Just take a look at this table. It's pretty amazing, right? We solved completely different problems, from counting employees to finding geometric shapes, but the core approach is the same. The hard part is always figuring out what state to track as you sweep. And look at that time complexity column. ON log n, ON log n, ON log n. That's no coincidence. It tells you that the bottleneck, the part that takes the most time, is almost always that initial sort.
So, when you're revising, keep these tips in mind. Number 1, that ON log n is almost always your answer for time complexity because of sorting. Number 2, and this is the most important part, focus on defining your events and your state. If you can get that right, you've pretty much solved the problem. And number 3, don't be afraid to think outside the box. The line doesn't always have to be vertical. The real challenge is learning to see problems through this sweep line lens. Once you master that, you've got an incredibly powerful tool in your back pocket. Thanks for watching.